Okay, so let's have a quick look at gravitational potential energy. So we've got two 20 kilogram masses here, and let's assume we're on Earth. Although, to be honest, this guy's 8 meters tall, we might not be. Who should be most frightened, right? Obviously, this guy's going to be more worried. This block has got a lot more energy stored in it, and when it falls, gravity will do work upon it. The force of gravity will do work upon that mass and increase its velocity, therefore increasing its kinetic energy. This thing's going to be going a lot faster. When it hits him on the head, it'll probably kill him. This guy's going to get hurt, possibly killed as well, who knows. Let's have a look at the sums, right? So what we want to be thinking is how much work would have taken to get this block into that place, into that position in the first place. So we're going to take the example we took from the work video. Okay, so let's start by thinking about how much work would have been required to raise this 20 kilogram block by 20 meters. Okay, work is force times distance. So how much force would I have to apply to just hold the 20 kilogram block? Well, if you did 20 the mass times acceleration due to gravity, you'll get the force required to just hold it steady, right? If it's sitting still on the top of the building right now, that's the force that is being pushed up right now. Okay, so you've got a force directly up of approximately 200 newtons, because gravity on Earth is about 10, and you've got the weight acting down, which is also about the same size. So these two arrows should be about the same size. Now, we use a simplification. We say that the force required to lift the object is just mass times gravity. Initially it's slightly more, and at the end when it's slowing down it's slightly less, so we can just use that assumption. Okay, so in order to work out the work done in raising this block to this height, we do force times distance. The force is given by mass times acceleration, and the distance is just the height. Right, so I've just said that in words here, and essentially we can rewrite the work equation as gravitational potential energy is equal to the mass times acceleration due to gravity times by the height. So if we have a look for our for our yellow guy, he did, I'm subbing the numbers into the equation, he carried 40 kilograms in a gravitational field of 9.81 newtons per kilogram, and he lifted them by 10 meters, and so he did this much work. Okay, the blue guy did only 20 kilograms, but he went twice as far, and therefore he's done exactly the same amount of work. Okay, so now let's have a look at that small assumption we made at the beginning and why it's useful to look at it on a force time graph. Okay, so like we said, if this is a 20 newton weight, there'll be a force of 20 newtons acting down, right? And you'd have to apply not 20 newtons, but a minimum, I don't know, just slightly more, 20.1 newtons, right, to get it going. If you apply just 20 newtons, then this force and this force balance each other exactly, and you've got equilibrium. It's not going to move, right? So there's an assumption going on. All right, so we're going to just explain that, talk about that a little bit. Okay, so let's say that you do, right, instead of applying a force of 20 newtons, you apply a force of, let's make it a bit larger, 23 newtons, right? Now you've got a net force up, right? You could redraw this force diagram as just this. Is your object, and there's a force of 3 newtons acting up. You've got unbalanced forces, the thing will start to accelerate, okay? Now, you're trying to raise this thing 20 meters, it's going to get faster and faster and faster, you don't want it to go too fast, so you ease off, and you just push, you drop your force down to just 20 newtons, right? So the net force becomes 0. Right? Whoops. But now the object is moving. It's got some velocity, but the forces are balanced. If forces are balanced, then velocity remains constant. So we're going back to Newton's laws. So you can think of it like this, right? If this is your 20 Newton force, right, and this is the 20 meter distance that's going to be needed to be travelled, right? Initially, you don't apply 20 newtons, you apply a little bit more than 20 newtons, right? You ease the force off when the object gets going, you apply a constant force for the rest of the distance, and then at the end you're going to bring this object up to here, say, and you want to just let it rest on top of whatever you've lifted it onto. So you ease off on the force. Now you've got unbalanced forces in the opposite direction. If you make this force, say, 17 newtons, right? Now the free body diagram would look like just 3 newtons acting down. The object decelerates, and hopefully you can just lift it and it will stop dead at the top. Now, if we look at the graph, right? Force, distance, this area represents the energy expended in doing this task, and this little chunk of extra effort here will fill this little chunk of unrequired effort at the end because it had some momentum, right? So essentially you can treat it as though it's just a straight line, and that's why we don't bother with any of that. You can forget all of this business and you just treat it as though you just lift it with 20 newtons throughout. Okay, although initially the force is slightly greater. Okay, I hope you found this video useful. If you have any comments, questions or corrections, please make them on the comments. Thank you for watching.